Stellar mass black holes. This is the most common black hole in the universe, and the most personal, because if a star like our Sun were just a few times bigger, this is how it would end. A stellar mass black hole is born from collapse, not quietly, not slowly, but in a cataclysm. A supernova tears through space. The outer layers of a dying star explode outward at a tenth the speed of light. But the core, what's left behind, caves in. Gravity does what it always does. It pulls. But this time, there's no resistance, no pressure strong enough to hold it back. Atoms collapse, protons and electrons merge into neutrons, and then, even those can't survive. The mass doesn't disappear, it condenses, all of it, crushed into a single point, a singularity. What's left is a black hole, with a mass anywhere from 3 to a few dozen times that of our Sun, but packed into a space no larger than a city. Invisible, silent, utterly black. You don't see it. You feel it. Its presence warps the light of stars behind it. Gas spirals inward, heating up, glowing in X-rays just before it's lost forever. Like a cosmic warning flare. This is how we find them. Not by looking at the hole, but at what falls into it. One of the first ever discovered, Cygnus X1. It pulls on its companion star like a predator in orbit. We can't see the black hole itself, but we see the star dancing around something invisible. And we know, stellar black holes are everywhere, scattered throughout galaxies like seeds from dead giants. By the time we finish this sentence, several may have formed somewhere in the universe, because stars die all the time. And sometimes, they don't just die, they collapse into silence. Intermediate mass black holes. This is the missing link. A cosmic ghost we only recently started to believe in. Intermediate mass black holes shouldn't be rare. They sit right between stellar black holes and the monsters at the galactic centers. Their mass? Hundreds to hundreds of thousands of suns. Too big to be made from a single star, too small to anchor a galaxy. So where are they? For decades, astronomers looked and found nothing. No clear signs, no gravitational tugs, only theories. They might form in dense star clusters, where collisions and mergers happen fast. A black hole consumes stars. Another joins it. They snowball, quietly growing over millions of years. Then, in 2009, we found a candidate, a flicker of X-rays from a distant galaxy, HLX-1. It didn't behave like a stellar black hole. Too bright, too massive. It looked like the echo of something bigger. Something just past the threshold. This was different. This was in between. And in 2020, gravitational wave detectors picked up the signature of two black holes merging. One of them was massive, but not supermassive, about 142 solar masses. Right in the sweet spot, proof that intermediate mass black holes are real. They're still elusive. They hide in the shadows of galaxies. Not big enough to command them, not small enough to be ignored. Think of them like the teenagers of the black hole world. Not quite grown, not quite new, just waiting to be noticed. Supermassive black holes. At the heart of nearly every large galaxy, something waits, something ancient, immense, and utterly quiet. A supermassive black hole. Not millions, but billions of times the mass of the Sun. They don't orbit, they don't drift, they anchor. Galaxies form around them like whirlpools in space. We don't know how they got this big. Some say they were born early, seeds from the first stars, growing fat off the gas and dust of the infant universe. Others think they're the result of countless mergers. Black holes swallowing each other in the dark. What we do know is this: they rule. Sagittarius, a star, lies at the center of the Milky Way. It's quiet now, but we can see stars whipping around it at impossible speeds, orbiting a point that emits no light. Nothing else could hold them in place. Nothing but a black hole, 4 million suns, compressed into a region smaller than Mercury's orbit, and that's not even close to the largest. TON 618. A black hole 66 billion times more massive than the Sun. If the solar system were placed next to it, it would vanish inside the event horizon like a grain of sand dropped into the ocean. But supermassive doesn't always mean visible. When they feed, they blaze. Gas and dust swirl around them in accretion disks, heating to millions of degrees. Some light up as quasars, beacons from the edge of the observable universe. Others, like ours, sleep, dormant, but always there. Supermassive black holes shape galaxies. They sculpt star formation. They can launch jets of energy that pierce through intergalactic space for millions of light years. They are not stars. They are not explosions. They are structures, permanent and vast. And every time you look up into the night sky, you're looking at galaxies orbiting monsters. Some galaxies even collide, and when they do, their black holes spiral toward each other and merge, sending gravitational ripples across the fabric of space-time, tiny distortions that we can now detect. The universe speaks in those ripples, and what it tells us is that black holes are not exceptions. They're foundations, primordial black holes. Before galaxies, before stars, before light, there may have been black holes, not born from death, but from pressure, from the universe itself, when it was less than a second old. These are primordial black holes. They weren't formed by collapsing stars, because stars didn't exist yet. They emerged from density, from chaos. Right after the Big Bang, space was not empty. It boiled, with energy, with temperature, with fluctuations. Some tiny pockets of matter, just a bit denser than their surroundings, may have collapsed under their own gravity. And if they were dense enough, they formed black holes the size of an atom, with the mass of a mountain. 1 billion tons packed into something you could hold in your hand. If you could hold it, you can't. They'd be invisible and nearly undetectable. No light, no X-rays, no gravitational tugs on nearby stars, but they might still be here, wandering the universe like silent relics from the beginning of time. Billions of them, maybe, passing through planets, through stars, through us. Some scientists believe they could be a candidate for dark matter, the invisible substance that holds galaxies together. Not particles, not fields, but black holes. Old ones, tiny ones. We've never seen one, not directly. But there are hints, gravitational lensing, when a small object bends light from a star behind it. One such flash, just milliseconds long, could be a whisper of a primordial black hole passing between us and the light. If they exist, they'd be older than the oldest galaxy. They'd be fossils, not of life, but of creation itself. And if even one were captured by Earth's gravity, it would pass through us again and again, silently, unstoppably, not causing explosions, not making craters, just punching through matter like it wasn't even there. Because gravity doesn't care about size, only mass. And these things, for all their mystery, have plenty of that. Micro black holes. These are the black holes that shouldn't exist, but might. Not formed in space, not created by stars, but by energy, pure concentrated energy. A micro black hole is smaller than a proton, not because it's less massive, but because it's so tightly packed, so infinitely dense. Its event horizon, the point of no return, is almost unimaginably small. According to theory, if enough energy is focused into a single point, even briefly, it could curve space enough to form a black hole. Not in a star, not in a nebula, but in a lab. This idea shook the world when particle colliders like the Large Hadron Collider, LHC, came online. What if smashing protons at nearly the speed of light created a black hole? For a moment, headlines panicked. Will the LHC destroy Earth? Nope, it won't, because even if a micro black hole were made, it wouldn't last. That's the thing, micro black holes evaporate. Thanks to a quantum effect known as Hawking radiation, named after Stephen Hawking, black holes, especially small ones, lose mass over time. They bleed energy, they fade. A stellar black hole might take longer than the age of the universe to evaporate, but a micro black hole, it might vanish in a fraction of a second. Gone, almost as soon as it forms. In its death, it would release energy, but not enough to harm us. It would be over before a human brain could register it. A whisper of heat, a quantum ghost. Some believe the early universe may have birthed micro black holes alongside primordial ones. Tiny, fleeting, never surviving more than a heartbeat of cosmic time. But others think they might still form, in high-energy collisions, in the cores of neutron stars, in dimensions we haven't discovered yet. Because here's the twist. Micro black holes may be evidence of other dimensions. In theories like string theory, gravity might leak into hidden dimensions, making it stronger at very small scales, stronger enough to collapse energy into a black hole, not in space, but in a subatomic landscape. It's still speculation, but science doesn't dismiss it. We look, we listen, because if we ever create or detect one, we may not just understand black holes better, we may understand reality better. Exotic black holes. These are the rule breakers, the what-ifs, the edge of imagination, grounded in real physics. Exotic black holes aren't defined by what we've seen, but by what the laws of physics allow. And some of them are strange, truly strange. Take the Kerr black hole. It spins. That might sound ordinary, but in astrophysics, spin changes everything. A non-rotating black hole just swallows. But a rotating one? It twists space-time like water going down a drain. This twist creates an ergosphere, a region outside the event horizon where space itself is dragged along with the black hole. Inside the ergosphere, you can still escape, but you have to move faster than space is being pulled. You're fighting against the flow of reality. In theory, you could extract energy from this spin, drop something in, catch it on the edge, pull some energy back out. It's called the Penrose process. A black hole, not just as a sink, but as a battery. And that's just the beginning. There are Reissner-Nordstrom black holes, electrically charged, not just pulling matter, but interacting with it. In theory, they might create different event horizons, multiple layers of no return. Complicated, delicate. Not likely to exist in nature, but possible in theory. Then, there's the weirdest of all. Wormholes. Some solutions to Einstein's equations allow for a black hole that connects to another point in space-time. A bridge, a shortcut, a tunnel. You fall into one side, and maybe, just maybe, come out the other. No evidence exists that such black holes are real, but mathematically, they're allowed. If certain conditions are met, if exotic matter with negative energy density exists, and if space-time doesn't collapse under its own paradoxes. Even more speculative, white holes, the reverse of black holes, where nothing can enter and everything must escape. They might be the other side of a black hole, or the final phase of Hawking radiation, or just an elegant mathematical dead end. But these ideas keep physicists awake at night, because if we find one, even just the signs, it would rewrite our understanding of time, causality, and maybe even death. They don't just devour matter, they devour assumptions. Now you've seen the spectrum, from black holes born in stellar deaths, to giants at the hearts of galaxies, to relics from the Big Bang, to theoretical whispers of other realities. Some are real, some are hypothetical. All of them stretch our understanding of physics and ourselves. Because black holes aren't just objects. They are questions, wrapped in gravity, echoing through space-time.